Hello again. Today we're continuing our discussion on polar equations and polar functions, and today we're going to be talking specifically about the derivatives of those polar functions. So let's get started. With polar functions, we need to remember that theta is the independent variable and r is going to be the dependent variable. So when I write the derivative, it's going to be dr d theta. I'm going to find the derivative of r with respect to theta, and I can also call that r prime of theta. Well, what does that actually mean? Well, if r is the distance from 0, 0 out to the curve with a straight line, then dr d theta is going to measure the rate at which that distance is increasing or decreasing. So for example, if I have r equals the sine of theta over 3, and there's the graph of it right there, by the chain rule, if I take the derivative of this, I'm going to get that dr d theta equals 1/3 times the cosine of theta over 3. And the derivative of this is going to equal 0 when theta is 3 pi over 2. So basically I'm trying to figure out how is dr d theta changing as I go through the graph from 0 all the way to 3 pi for this graph. All right, so for all of the values from 0 to 3 pi over 2, I just plugged in random values of theta into the derivative, and I got that the derivative was positive. And similarly, when theta goes from 3 pi over 2 to 3 pi, I just plugged in random numbers into the derivative for that as well, and I got that the derivative was always negative. So what that means is as I draw the graph, and I've kind of retraced it in green, from 0 to 3 pi over 2, I notice that the distance from the center is increasing. And I've drawn little arrows there so that you can see that it actually is increasing. And then from theta, for theta going from 3 pi over 2 all the way back to 3 pi, which is where it started, that distance now from the center to the graph is decreasing. And there's little arrows that kind of show that as well. So we're not going to use words like closer to or farther from, because remember, there's the possibility for negative r values. And we'll talk about how to deal with those in class. All right, for slopes of tangent lines, remember, the slope of a tangent line is still considered to be dy dx because we want to know how quickly y is changing as x changes a little bit. But for the sake of the graph, we're dealing in r's and thetas. So how do I get from r's and thetas into y's and x's? Well, remember, there were two formulas that I used to convert r and theta into x and y, and those were x equals r cosine theta and y equals r sine theta. So if I treat dy dx like a fraction, I can divide top and bottom by d theta, and I will get dy d theta over dx d theta. And I can do that because x and y are both expressed in terms of theta, because I know that r is a function of theta, and the other half of each of those is also a function of theta. So what I do is if I take the derivative of y with respect to theta, knowing that each half of r sine theta is a function of theta, I have to use the product rule. So the derivative of r is dr d theta times sine theta plus r times the derivative of sine theta, which would be cosine theta. And doing the same thing for x, the derivative of r is going to be dr d theta times cosine theta plus r times the derivative of cosine theta, which is negative sine theta, and that's how that minus gets there in front of the second term. So I've got expressions for dy d theta and dx d theta. So now I can figure out dy dx, because that is dy d theta over dx d theta. I can take each of those expressions, put dy d theta on top, dx d theta on the bottom, and that is my official formula for the slope of a tangent line for every polar curve. So you may want to write that down. That's a formula that we are going to use a lot. All right, so for example, if I have r equals the sine of theta over 3, like you see on the graph, we saw that earlier in this video, dr d theta is going to be the derivative, which we calculated before as 1/3 times the cosine of theta over 3. So if I know that dy d theta is dr d theta sine theta plus r times the cosine of theta, I can replace every dr d theta with 1/3 cosine theta over 3, and I can replace every r with sine of theta over 3. And that's going to give me that formula right there. If I do the same thing with dx d theta, then I get 1/3 cosine of theta over 3 times the cosine of theta minus the sine of theta over 3 times the sine of theta. So dy dx then becomes my dy d theta over my dx d theta, and that's what I get. So if I specifically want to know the equation of a tangent line at theta equals pi over 2, well, I have a formula to calculate the slope of any tangent line on this graph. I just found it in the previous slide. So if I want the slope of the tangent line at theta equals pi over 2, I need to figure out where that point is first, because I am trying to find the equation of a tangent line, so I do need an x-coordinate and a y-coordinate. So my y is going to be r times the sine of theta, which is going to be 1/2 times the sine of pi over 2, which is going to be just 1/2. X is going to be r times the cosine of theta, which is going to be 1/2 times the cosine of pi over 2, which is 0. So the point that I'm looking at on the xy plane would be at the point 0 and 1/2 using x and y coordinates. There's the formula for dy dx that I found using just this function. And so if I plug in pi over 2, that's what I get. And I can calculate the sines and cosines of all of those angles. So that's what I'll do. I'll simplify things that actually equal 0. I'll cross those out because those aren't worth anything. And so what I'm left with is negative root 3 over 3. So I have an x of 0, a y of 1/2, and I have a slope of negative root 3 over 3. And if I put all of those into the equation of a line, I get that my line is y equals negative root 3 over 3 x plus 1/2. And that's the equation of that tangent line right there. All right, let's talk about horizontal tangent lines and how to find out where those are. So if a tangent line is horizontal, then the derivative is equal to 0. We know this when we were dealing with x and y graphs, x and y functions. So what that means is the numerator of the derivative would have to be 0. And that means that dy d theta would have to be 0. So that's really all I have to look at. When is dy d theta equal to 0? As long as dx d theta isn't equal to 0 as well. So there's where dy d theta is as its expression. And if I use r equals the sine of theta over 3 and dr d theta as 1/3 the cosine of theta over 3, then that's what I get, just like I got before. So when this equals 0, I get angles like 0, and you can see the horizontal tangent line there, 1.977. These are in radians, by the way, and there's the horizontal tangent line at 1.977, 4.712, which is actually 3 pi over 2, and then 7.448, and those are the spots where I have horizontal tangent lines. For vertical tangents, I know that the derivative is going to be undefined, and what that does is it makes the denominator 0, which means that dx d theta would have to equal 0 without dy d theta equaling 0 as well. So there's my dx d theta, and again I plug in my function for r and my function for dr d theta, and that's what I get. If I set all of that equal to 0 and using a calculator, I get that theta equals 0.8517, and you can see it there. 3.308, 6.116, and I'm drawing them on the graph as I go, and the last one is at 8.573. So there's 4 spots where I have vertical tangent lines on this graph. All right, and that is pretty much a good summary of derivatives for polar functions. If you have any questions, please let me know, and I will see you tomorrow.